First, I got 2 emails about meeting on campus next week. So we will meet in person in Brighton on Monday. And then Tuesday, we just meet online. Every Tuesday, we'll meet on Zoom. Monday, Wednesday, Friday, we're in Brighton, upstairs in, let me see.
I think it's like 2 something.
Yeah, 209. We have a chalkboard. Yay. Yes. And I was hoping to have like a little get together, you know, and we can have snacks, but we all have to have a face covering. I still think it's okay to have snacks, but you have to be like, you know, respectful of other people.
Eat snacks in the class?
Just for the first day. Something small. But also, again, we all have to have a face covering. And we're going to get to know each other a little bit. We might do a worksheet, you know, after we introduce ourselves. I might have you get together and work on something together. And other than that, we'll just do notes. We won't do a quiz next week, so don't worry about a quiz until we get kind of settled into the class in person. And I'm trying to finish up all my to-do things. One of them is to answer your homework questions. So I will do that as soon as I can. If I don't answer it today, I'll just add more time to your assignment so we can get your score, your full score. But try to do the homework by midnight tonight. And I'm probably going to make another homework assignment for you today and make it due next week on Friday. I want to keep working on 2.2. Then we're going to skip over and talk about 2.4, but 2.4 will not be on a quiz or a test. We probably won't even do homework on it, but I might have you work on that material as groups, like on a worksheet, and not graded, just for practice. Okay, any questions or concerns? Okay, I will write that down, extra time on homework, and I'll change your due date tonight, probably just add a few days. Anybody else? Okay. So I'm going to reintroduce how to find limits without a graph using vertical asymptotes. Then we're going to go through an example, and then we'll do a few more examples. And again, I want to talk about material from 2.4 just to help you understand what's going on. But it won't be on your test.
Wait, it won't be on our test? What do you mean?
Just material from chapter 2.4 is not going to be tested, but it is very important. So I will explain it, but you don't have to memorize it. We'll get there. And also, when we do have a test, we'll do a review day, so you know what kind of questions to look for. They're going to be very similar to homework questions, and we'll get practice, you know, getting ready for your test.
Wait, Cassie, quick question. On the test, we could use calculators, right? Like the scientific ones? Or is it a no?
You can. That's okay with me. You could also just leave it like root 2, just leave it how it is.
Okay.
But you cannot use your cell phone. So if you're using a cell phone as a calculator, I will tell you to put it away. But you can bring a little calculator. I've got a handful of them. I'll bring them to class. It's okay.
Okay, perfect. Thank you.
We had this part. computing limits that go to positive or negative infinity without a graph. Also, just thinking about your homework, on Monday, I'll bring my laptop, and if anyone's had trouble creating their account, you can come over to my computer. We can help you figure out how to get your homework set up. Or if you have a laptop of your own, you can bring it to class and I can come over and help you access homework. So for these limits, we're going to use vertical asymptotes. So it's like a function, f of x, looks like some other function, p of x, divided by a different function, q of x. You look at where q of x is equal to 0. But p of x is not 0. We're looking at f of x being the function 1 over x. So we have a vertical asymptote if x is equal to 0. So what we're going to do is just kind of look at the limit as x goes to 0 from the left and from the right. And I'm going to put a table of inputs, then we'll see what all the outputs are, and then we'll get the limit. Okay, we're inputting x values. And we get outputs that are y values or f of x values. So f of x here. Okay. And then I put in some numbers. I picked -1 to get started. X is equal to -1, f of x is 1 over -1, so we've got -1 as an output. We want to get closer to 0 from the left. So we're going to put in negative 1/2. So 1 over negative 1/2. And you're going to take that top number.
-2, right?
Reciprocal, get -2. Yes.
Yeah. Yeah, you could do the equation if you want, you know. Wait, never mind.
It's good. Thank you. Just to remind everyone, but when we put in a negative 1/10, we're going to get out -10. Be closer to 0 from the left, and we're putting in negative 1 over 1,000. I'm actually have 10,000. Put this to the function, we have a negative 10,000. Put in one more. Negative 1 over 1,000,000. That goes through your function, and the output is negative 1,000,000. So looking at x getting closer and closer to 0 from the left, f of x is going further and further to, like, is approaching negative infinity. Negative 1, negative 2, negative 10, negative 10,000, negative 1,000,000. It keeps going like that. Bigger and bigger negative numbers.
That would mean the slope or like the graph trends downward
Yes.
infinitely.
So we'll write that as the limit as x goes to 0 from the left. Of f of x is equal to negative infinity. Okay. Now we're going to approach 0 from the right. This way, we're going to start with positive 1 and then positive 1/2. Keep going. Okay, so it's positive 1, 1 over 1 is 1. Put in positive 1/2, we'll get out positive 2. Then I put in positive 1/10. It is I went over to 1/100th. Get out 100. Last one I put in is 1 over 1,000. function and get positive 1000. So this time, as x gets closer and closer to 0 from the right, f of x is increasing without bound to positive infinity. Okay. I'm going to do another example, similar but different. The function is f of x equals 1 over x squared. To look at vertical asymptote at x equal to 0, and then do the limit as x approaches 0 of f of x. You can put your function like this, or you can put it like that. I'm going to have this here. So when you go to 0 from the left, and then we square that number, it's going to be a positive value, and it's going to do like this one before. It's going to be like, put in -1, you're going to get out +1. Put in -1/2, we're going to get out +2. So we're going to go to positive infinity from the left. Same from the right. If you put in a positive number and then square it, it's still positive. And then you're going to take the reciprocal and get out values that are going up to positive infinity. So I've got a shorthand for this, and I'm going to try to explain this idea. So we're going to look at a number that's really close to 0, either on the negative side or the positive side. Either positive 0.00001 or negative 0.000. Okay. We put those through the function f of x. Either way, we're going to square it, and the denominator is going to be positive. And that number is some very, very, very small number. So what I'm going to write is a positive small number like this. So some positive number that's really, really, really close to 0, but we have 1 over this positive small number, which we looked at earlier, becomes a very big number. Very big positive number.
What do you mean by small?
Small, like almost zero, like very close to zero, like this.
Okay,
0.00001.
okay, got it.
And I'm gonna practice like explaining or do examples. So positive small is like very close to zero, and positive big is getting closer and closer to infinity, positive infinity. So I'll explain this with another example. In this example, f of x is x plus 3 over x times x minus 2. We're going to have a vertical asymptote if x is equal to 2 or 0. We're going to look at the limit as x approaches 2 from the left and then from the right. Starting with x approaching 2 from the left. And I'm going to put this function right here, x plus 3 over x times x minus 2. So we're getting really close to 2 from the left. So we're pretty much looking at the number 5 in the numerator. We're going to go ahead and put 5. Okay. This is pretty much 2. It's like closer and closer to 2. I think a quick sketch will help here. So we're just a little bit less than 2, not actually reaching 2. So some numbers slightly less than 2. And then minus 2 is going to be a negative small number. Like the difference between them is very, very small.
Wait, where'd you get the 5 from?
We get it from imagining that we're getting closer to 2. So this is a 2 right here. Plus 3 is getting closer to 5.
Okay. Thank you.
Yeah. And
Wait,
again,
can you say that again? I didn't catch that.
yeah. So this is getting closer and closer to 2. So it's 2 plus 3 is that 5 right there. So almost 5, but not quite 5.
Okay.
Same thing here. This is almost 2. So I have like 2 right here.
No.
But as this gets closer to 2 on the left, the difference between that number and the negative and minus the actual number 2 is very small, and it's negative. You have some number, divide it by some negative small number. We looked at this earlier. It's going to be a negative big number. Or negative infinity. Let's have x go to 2 or the right of your function. And we're going to see what the limit is for that function.
Wait, what do you mean by negative big and negative divided by negative infinity?
Oh, not divide by, negative big, or you could call it negative infinity.
Okay, yeah.
Thank you. All right. Limit as x goes to 2 from the right. This isn't like totally like official math from the book. This is my way of explaining what happens. So this time, we're going this way. And we're almost reaching 2, but not quite 2. We're like slightly, some numbers slightly above 2, like 2.0001.
I see.
So this is going to go in here, and we're almost at the number 5. Put this right here. It's like pretty much 2. Divide by that. Now we have a number that's a little bit bigger than 2, and then we subtract 2. So this difference is very small, but it's positive. Positive 5 over positive 2 times a positive small number will be a positive big number.
Tessie, what by plus small, it's like a positive small number that's close to 0, right?
Yes.
Okay, and the other one is a negative small, that's like any small number that's close to 0, like it goes from like -2 to -1 to negative 0.5 or something, right?
Yeah. So it's getting close, getting smaller and smaller and smaller, and it's also negative.
Okay. So by negative big, you're talking about like numbers like negative 0.001 or something?
More like negative 1 million and negative 2 billion.
Oh, okay. Something like that, yeah.
And then the other way is that's the negative small, negative 0.0001.
Yeah.
Okay, let me see what's in my notes. Oh, okay, last part is since the limit as we go to 2 from the left is negative infinity, then the limit as we go to 2 from the right was positive infinity. The limit as you approach 2 from both sides does not exist. I'm going to summarize that idea, and then I'm going to introduce one example, and that's the end of this section. when you're doing limits and you're getting something that's kind of like a number over values that are getting smaller and smaller. It's going to become bigger and bigger numbers. So let's just put, no, okay. Number over small is big. If you have a number over a very big number, like a number like 1, divide by some very big number, like 1 over 1 million, that's a small number. I'm going to do a quick example for each one and then move on. This one.
And the reason why a number divided by small equals a big number for, for the, for the concept on the top, right?
Yeah.
Yeah, I think that's the reason why, because like when you divide by like a 0 point something number, the number usually tends to get bigger, right?
Yes, yeah. As you get, yeah, these values get smaller and smaller, this output is going to get bigger and bigger.
Oh, yeah. Mhm.
Let's put the number 2. Never mind. Let's keep it easy. 1. 1 over something very small. Like 1/1000th. You would just take this reciprocal and get a positive 1,000th. Big number. That's my number. Divide by a small number, you get out a big number. Let's put some number 1 over a big number like 1,000. It's a very small number, 0 point, to be like 0001. Let me know if I'm wrong. I think I have too many zeros. Okay, I got it. By the way, I'm not, and I don't expect you to be a calculator. We all kind of have calculators now on our phones. What I want is for you to understand the concepts in each section. Right, and there's one little piece from this section that I want to talk about. It's just an interesting graph that you might see in the future. This is kind of just on the side. So this example is in this section of the book. This example was also brought up quite a few times while I was studying math. After completing calculus 1, 2, and 3, you could take an introduction to proofs class, so that once you take these topics again, you can prove the ideas. And this one was one that we worked with a couple times. It's the limit as x goes to 0. Of the sine of pi over x. And if you have f of x equal to sine of pi over x and put that in Wolfram alpha or Desmos, you'll get a nice graph. I'll do my best to sketch the graph. But what happens is the limit does not exist, and the graph will kind of help explain why.
Because like infinite curves or stuff like that, it's like goes up, down, up, down, up, down.
Yeah, it never actually lands on a number. It just keeps on oscillating, like you said. The sine of pi over x oscillates around x equal to 0.
Does not exist. Okay.
Oh yeah, thank you.
Thank you.
You're welcome.
Okay, so we want to label 0. It's going to give you a sec to write it down, but I want to use the full whiteboard to draw the graph. So it's the limit as x is approaching 0 of the sine of pi divided by x. Is not going to exist. It does not exist.
Same thing with cos and tan, right?
I think so. It happens. I'll check maybe after class. I think there's one or two other fun graphs that kind of do this, but I want to be sure I say the right thing. So I'll Google it. And I'll write that down. I'll let you know when we meet next time. We're just gonna, I definitely have the graph for this one. Gonna come up as high as 1 and as low as -1. So they're kind of like oscillating, and then it gets closer and closer and closer, and it starts to just bounce up and down forever right here. It never reaches x equal to 0. So as x gets closer and closer to 0, your function never stops. It keeps on going up and down and up and down, and the limit will not exist. There's no actual number we're going to land on. We're not going to go to positive infinity or negative infinity. We just oscillate. We're almost out of time. So,
Wait, when it comes to sign, wait, we never really land on 0. That's why, right?
yeah, it keeps going up and down.
Okay.
And yeah, it gets closer and closer, like these little.
Yeah, this is like, oops, yeah, yeah, yeah. It does really, it just keeps going up and down, and it doesn't really, like, stop at a point.
Okay, I would like to introduce the next section, but we'll have to wait till we meet together to actually work on it. And we're going to jump over to 2.4. Again, I won't put questions from 2.4 on your test, but I think it's important that we talk about it.
Wait, isn't there a 2.3?
There is, and I'll do that after 2.4.
Okay.
Yeah, we'll go back, but I want to skip over to the precise definition of a limit.
Okay.
I'm going to start a graph. When we meet next time, I'll put the graph on the board while you're all talking and getting to know each other. And when we get to doing notes, we'll take a look at the picture and then write down this definition. We're going to mark some x value, call it a. And over here, we have a number L. And our function has a hole right there. Point AL, well, there is no point AL. And then it just kind of swoops along like this. We'll call our function f. And I'll explain the limit as x approaches a of f of x being equal to L. Using the definition. Okay, that's it for today.
Also, I would like to go help us answer a question about instantaneous velocity. Can you like do a question about instantaneous velocity, because it's on our work and it was kind of confusing when I did it. So I'm still trying to understand what it means. So can you like do like a question about it, or like two?
Sure. Let's do it when we meet on Monday, or because we're out of time, I think.
Yeah, but you can stay after, like a
Yeah.
few minutes after class, right?
Yeah, just hang it after class and you can work on your homework.
Professor,